Now let's turn to page 4 of the handout section 2. Here, this is one of the most important slides in this class. So pay special attention, and you might want to revisit a couple of times. So on the right, I show two pulse programs. The upper one's called DP, and the lower one's called CP. DP stands for direct polarization, which means if we are going to do carbon, we directly excite carbon. And cross polarization is taking a detour. We're going to detect carbon, but we're going to excite proton first, and then we are going to cross polarize carbon from proton. So if you look at the pulse program on the top, the DP one. From our initial simplest pulse program, now it's a little complex. So we are having two channels now. So there's a proton channel, that's carbon channel, and the horizontal axis is a time axis. So in the beginning, nothing happens in both channels, and then there's this peg showing up on the carbon channel, a 90-degree pulse, and nothing yet on the proton yet. So after the 90-degree pulse on the carbon, we know carbon magnetization gets excited, which means the pulse turn the carbon magnetic moments from z direction to the horizontal plane. So we change the I sub z to I sub x at the end of the pulse. And then we are going to detect the carbon signal as shown by the wave. And when we detect on the carbon, we turn on the pulse on the proton channel, and that's called the decoupling pulse. It's just there's no trick on the pulse. It's just a very simple pulse. It's just turn on very, very long. It's during the entire detection period. We just turn on the proton and the effect. So you will need some like quantum mechanics to show that the decoupling actually removes the dipole coupling between proton and carbon. But for now, it's good for you guys. Just remember that when you turn on a proton pulse, you remove the dipole coupling, and you're gonna get a carbon signal that's free of this proton-carbon dipole coupling. So that's the essence of a direct polarization or DP experiment. And the bottom pulse program, CP, is a little more complex, but let's just take a look along the time axis. So in the beginning, nothing happens, and we have I sub z, which is all the magnetic moments are on the z direction. And then we're applying a 90-degree pulse on the proton channel. So at the end of the 90-degree pulse, what we're going to have is a proton magnetic moments that turn onto the xy plane. So we note that by I sub x. Then what happens is we are going to turn on a strong pulse on both proton and the carbon channel. That's called the CP pulse, the cross polarization pulse. And this pulse usually is kind of maybe a couple of milliseconds, let's say. So during this couple of milliseconds, what's happening there is carbon and proton, the magnetization will exchange signal, and we're going to get carbon signal from the proton. So at the end, we are gaining enough carbon signal from the proton, and then we're going to turn off the CP pulse, and we are gonna detect on carbon. And when we detect on carbon, we apply a pulse on the proton channel. It's called the decoupling pulse. So that's the same one. That's the same purpose as you see on the DP. So during detection period, proton decoupling and carbon detection, and the decoupling pulse is slightly taller than the CP pulse, which means that the pulse power is somewhat stronger than the CP power. So this is the CP pulse sequence. So it's still very simple. You borrow carbon signal from proton, and the very important benefit that we get from cross polarization is that during the CP, what you get is the enhancement of the carbon signal by a factor of 4, which is a big deal. If we can enhance signal strength by a factor of 4, we reduce our experimental time by a factor of 16. So it's a big deal. The factor 4 comes from the gyromagnetic ratio. So proton has a gyromagnetic ratio that's a factor of 4 greater than that of a carbon, and that's where this carbon factor of 4 coming from. Yep. So that's our two most important solid NMR techniques. These two are like your regular carbon and proton experiment on the solution. So we use these two all the time, and sometimes a variation of these two. And during the entire measurement, we spin a sample at high speed, usually greater than 3 kilohertz. We spin it to remove dipole coupling. So to remove chemical shift anisotropy, we use decoupling to remove carbon proton dipole coupling. Then we use cross polarization to remove to enhance the signal. Yeah, you might ask, if we have the CP to enhance signal, why do we still need DP? Oh well, DP has its own special use, as we will see. So again, a very important slide. Yeah, so now we turn to the next page. That's page 5. So this is a carbon-13 CP/MAS, so cross-polarization magic angle spinning spectrum of a polyurethane urea sample. So here, so you have so this is not too different from a carbon-13 solution state spectrum. So you have sharp peaks. You have you have your aliphatic signals, carbon signal between 0 and 50 ppm. You have your ether carbon signal at about 71 ppm. Then you have a aromatic signal between 110 and 150. The 155, so the peak at 155 ppm, I think that's a urethane carbonyl. And then there's a bunch of low signal around 200 ppm. I mark as with a asterisk, so that's the spinning sideband of the aromatic signal at around 130 ppm. So other than the spinning sidebands, everything else looks pretty much similar to a solution carbon-13 spectrum. Well, it's not as nearly as sharp as a solution spectrum, but often can give us quite adequate chemical structure information. and the spinning speed for the sample is 5,000 hertz. So you see that here we used cross polarization, and we can get this kind of a quality spectrum within probably like 10 minutes easily. So good signal strength. We removed the carbon proton dipole coupling, and we removed the chemical shift anisotropy. So with those few tricks, we get a decent quality spectrum.